Backtracking technique. The backtracking technique explained here uses the state space tree. I'm Efina and I'll be presenting you this topic. The topics of discussion in this presentation are: what is a state space tree, what is a backtracking technique, and 3 example problems using backtracking technique, which are the n-queens problem, the Hamiltonian circuit problem, and the subset sum problem. What is a state space tree? A state space tree is the tree of the construction of the solution from partial solution starting with the root with no component solution. The nodes of the state space tree reflect specific choices made for solution's components. A node is said to be promising if the partial solution is still feasible. Anytime the partial node becomes infeasible, the node called non-promising, the branch will no longer be pursued. Algorithm technique using state space tree are the backtracking technique and the branch and bound technique. Let us see how state space tree is used in backtracking technique. What is a backtracking technique? The principal idea of backtracking technique is to construct solution for one component at a time and evaluate each partially constructed components. If a partially constructed component can be developed further without violating the problem constraint, then it is done by taking the first remaining legitimate option for the next component. If there is no legitimate option for the next component, no alternatives for any remaining component is considered. How is a state space tree is used in backtracking technique? The root of the state space tree represents an initial state before the search for a solution begins. The nodes of the first level in the tree represent the choices made for the first component of a solution. The nodes of the second level represent the choices for the second component, and so on. A node in a state space tree is said to be promising if it corresponds to a partially constructed solution that may still lead to a complete solution. Otherwise, the node is called non-promising. Leaves represent either non-promising dead ends or complete solution found for the algorithm. The n-queens problem. The n-queens problem is to place n-queens on an n by n chessboard so that no two queens attack each other by being in the same row or in the same column or on the same diagonal. So given here is a diagram of a 4 by 4 chessboard, and each queen is placed in a row such that no two queens attack each other. Let us find one among the solutions to 4 queens problem using backtracking. Start with the empty 4 by 4 chessboard and then place queen 1 in the first possible position of first row, which is in column 1 of row 1. Then place queen 2 in the second row. After trying unsuccessfully in column 1 and 2, its first acceptable position is square in row 2 and column 3. This proves to be a dead end because there is no acceptable position of queen 3 in the third row. So the algorithm backtracks and puts queen 2 in the next possible position, which is the square in row 2 and column 4. Then queen 3 is placed at the square, row 3 and column 2, which proves to be another dead end because the fourth queen has no possible squares to be placed in row 4. Then the algorithm backtracks all the way to queen 1 in row 1 and moves it to the square in row 1 and column 2. Queen 2 then goes to the square, row 2 and column 4, and queen 3 is placed at row 3 and column 1, and queen 4 at row 4 and column 3, which is one among the possible solution to the 4 queens problem. The diagram given here shows part of a state space tree which helps to arrive at one among the solutions to the 4 queens problem. As you would have noticed, each level of the state space tree represents the placement of a queen at a particular row. At level 0, at the root, no queens are placed on the 4x4 chessboard. Level 1 represents the placement of the queen in the first row. It shows only part of the state space tree where the first queen is placed at row 1 at column 1 and column 2. Let us proceed the path where the first queen is placed at row 1 column 1. When the first queen is placed at row 1 and column 1, the second queen available position at row 2 are column 3 and column 4. When the second queen is placed at column 3 in row 2, it proves to be a dead end because for queen 3 there is no possible position at row 3. Hence, the algorithm backtracks to the previous level where only the first queen is placed and moves towards the solution path where the second queen is placed at row 2 column 4. This provides a solution path where the third queen could be placed at row 3 and column 2. This again proves to be a dead end because queen 4 has no possible position at row 4. Hence, the algorithm backtraces to the root and opts for the next solution path where queen 1 is placed at row 1 and column 2. This provides a solution path where queen 2 could be placed at row 2 and column 4, and queen 3 could be placed at row 3 and column 1, and queen 4 could be placed at row 4 and column 3. This is one among the solutions to the 4 queens problem, and expanding the state space tree would provide all the solutions to the 4 queens problem. 10 solutions for the 5 queens problem is given here. These solutions could be derived by constructing a state space tree. The Hamiltonian circuit problem. A Hamiltonian circuit is a circuit that visits every vertex once in an undirected and unweighted graph with no repeats. Being a circuit, it must start and end at the same vertex. The backtracking algorithm could be used to solve the Hamiltonian circuit problem. The backtracking algorithm uses a state space tree to find the Hamiltonian circuit given an undirected and unweighted graph as input. Let us find the Hamiltonian circuit in a given undirected and unweighted graph. The graph consists of 6 vertices which are labeled as A, B, C, D, E, and F. Let us apply backtracking technique to find the Hamiltonian circuit starting at vertex A. Make vertex A the root of the state space tree. The first component of our future solution, if it exists, is a first intermediate vertex of the Hamiltonian circuit to be constructed. Using the alphabet order to break the three-way tie among the vertices adjacent to A, select vertex B, and from B the algorithm proceeds to C, then to D, then to E, and finally to F, which proves to be a dead end. So the algorithm backtracks from F to E, then to D, then to C, which provides the first alternative for the algorithm to pursue. Going from C to E eventually proves useless, and the algorithm has to backtrack from E to C and then to B. From there, it goes to the vertices F, E, C, and D, from which it can legitimately return to A, yielding the Hamiltonian circuit A, B, F, E, C, D, and A. To find another Hamiltonian circuit, continue this process by backtracking from the leaf of the solution found. The backtracking is enabled by the structure of the state space tree. The subset sum problem. The problem statement of the subset sum problem. Find a subset of a given set A consisting of elements a suffix 1 to a suffix n of n positive integers whose sum is equal to a given positive integer represented by the variable d. For example, for the set A consisting of elements 1, 2, 5, 6 and 8 and d equals 9, there are two solutions to the subset sum problem, which are the subset consisting of elements 1, 2 and 6 and the subset consisting of elements 1 and 8. To solve the subset problem, it is convenient to sort the set's element in non-decreasing order to solve the subset sum problem. It is assumed that elements of set A consisting of a suffix 1 to a suffix n are arranged such that a suffix 1 is less than a suffix 2, which is less than a suffix 3 to a suffix n. The subset sum problem is solved for the given set A consisting of elements 3, 5, 6 and 7. The sum of the subset elements must be equal to 15, which is represented by the variable d. The state space tree used to solve the subset sum problem using backtracking technique is binary. The root of the tree represents the starting point, that is, when the sum of the subset elements is 0, representing none of the elements are included in the subset. It is an empty set. The roots left and right children represent respectively the inclusion and exclusion of the first element in the set A, which is 3. So when 3 is included in the subset, the sum of the subset element is 3 and when 3 is excluded from the subset, the sum of the subset elements is still 0. So the node value represents the sum of the elements in the subset. Each level in the state space tree represents the inclusion and exclusion of successive elements in the set. Thus, a path from the root to the node on the ith level of the tree indicates which of the first I elements are included or excluded from the subset. The sum of the included elements are recorded as the node value. If the node value is equal to D, then the solution to the problem is arrived. The tree is built until the last element of the set. So at the leaf, if the sum is greater than D or if the sum is less than D, the solution is ended as non-promising. But at the leaf, when the sum is equal to D, the solution is arrived and that node is a promising node. So applying the method described, the solution to the given subset sum problem is the subset 3, 5, and 7. To summarize, in this presentation, we discussed how state space tree is used in backtracking technique. We found solutions to 3 problems, namely the n-queens problem, the Hamiltonian circuit problem, and the subset sum problem using the backtracking technique. Thank you.